will show it this in much more detail. So we do a floor plan of the basic elements, then we do a power plan. So basically every multiplexer or every logic gate has a VDD and a ground that it needs to be connected to because it needs power. Right? So how the power rails have to flow all across the chip. So how is the power mesh flow? There is a black. That is done at this point. Okay. After this, after the power plant routing is done, the next is the placement and optimization. So in the placement, it will try to fit whatever logic you have given in the. So this is you have completed the power plant. Then you are doing the placement here, and in placement you are just keeping the small blocks. Yeah, you are not doing anything else. And then you perform the CTS because now you have connected the VDD ground. Similarly, you need a clock signal also for all the sequential elements like flip-flops. They require a clock. They require a clock signal also. So you will route the clock signals to every flip-flop in the design. Okay. So we have connected. So now, until now, what we have done? We have done the power connections. We have cleared the logic, and then we have done the clock connections also. Okay. Then what we do is the signal routing. So routing is nothing but now these write enable, write data, read data. So these are the signal routing that is happening at this stage, at the last stage. Okay. Once so finally you have connected clock, you have connected these signals, and you have connected the power signals also, right? After that is done, you go into the physical verification. So DRC, LBS is nothing but an antenna checks. So these are what they form the physical verification part of the we call it the ASIC design. So DRC is nothing but design rule check. So only will give you certain design rule checks that between two transistors you should have at a minimum this much gas. Okay. So you should have this distance minimum. If you flout that or if you violate that DRC, it will not. This chip is not production work. Okay. So you cannot take out with that. It will not function correctly. So that is design rule checks. LBS is nothing but layout versus schematic. Whatever. So for layout versus schematic, it is nothing but an equivalence check. That whatever is in the is going in the schematic, and whatever schematic it received is the same that is going in as the layout. So it is like a functional check that if the RTL is matching or the netlist here, this netlist is actually matching what we are implementing. And antenna checks are something where you might pick up some maybe you will do some you will pick up some noise. Okay? If you have very long wires running in the chip, then they are very susceptible to interference. Okay. So for those kind of things, we have to do some antenna checks. Okay. Now, if you see here, there is a power integrity and there is a crosstalk check being performed. So let me power integrity is being performed. What is power integrity? So, whenever your chip starts, will power up the chip. Right? All the transistors start simultaneously. Right? But so your power line, let us say it is 0.9 millivolts or 0.8 millivolts. Typically we use a 0.8 millivolt inside the chip, and very low signal. So if there are million gates that start simultaneously, what will happen? The 0.8 millivolts will trip, right? So you cannot start the entire chip at the same time. So power integrity has to be performed to make sure that you enable power to the chip in stages. Okay, so power integrity, you will start this part, you will start this part, you will start this part, so that the power supply load is not very high. Otherwise, the circuit will not perform. Right? You start everything in one load. You must have seen at your home also. The moment you put on some geyser or maybe microwave to light beams or that's an option. So that is the voltage bridge. If the voltage bridge comes, the circuit becomes bad. Right? It cannot perform anymore. So whether and when power integrity is being performed, along with that the crosstalk is also being performed. So crosstalk is like if two signals are running parallel, okay, what might happen is that if one signal is continuously being, let us say one signal is continuous 1 and the other signal is probably 0, 1, 0, 1, 0, 1, 0, 1. What happens is that the signal which was continuously set starts to interfere with the 0, 1, 0, 1, 0, 1. And it might happen that it interferes with the signal and makes it also 1 for more than, let us say, so by definition we wanted alternate clock 0, alternate clock 1. But due to interference, what will happen? You might see that, okay, it is set for 3 clocks together and then it deaccelerates. Okay, so then the signal functionality is failed. So those kind of checks we will perform at the crosstalk. Okay. Then comes, okay, so here we have done the DRC LDS. Okay. Now after we have done the routing, okay, what we do is we take out the netlist. We take out the netlist again here. Okay. This netlist. So this netlist is the output netlist of backend. This netlist is the input netlist to backend. Right? We have two netlists. One is input to the backend state, one is the output of the backend. So again, this output netlist is again simulated using the same test that whether it matches the functionality, whether it is doing what or has backend. If backend has done something wrong, then that test will not operate. Right? It will fail. So the same thing is being done again in the post-layout simulation. We call it this is the post-layout simulation. Okay. So we do the post-layout simulation and we again confirm that okay, the circuit is working fine. If the circuit does not work as expected, we have something called as an ECO. Okay, where ECO means it is a engineering change order. ECO full form is engineering change order, and we perform a gate level fix in the netlist. We don't modify the RTL anymore. Okay. We take the gate level netlist and we update the gate level netlist itself. And let us say some gates are added, some more gates are added, and then the ECO is performed. And then you again send it to post-layout sims, and then you again confirm that whether this logic is. So from here, so there is a loop here. Okay. Similarly, if the again we do a static timing analysis also. If the static timing analysis fails here, then we have to go back to this stage. Okay. So from here again a timing check is being performed that whether the circuit is again working at the desired frequency also. most of the times, if physical design has done its job correctly and still static timing analysis failures you are seeing, then you need to update the ATAL, which means that you have to start from that top again. So it's a long loop. So you will use time. Okay. So that is why it is very important for you to design it in a way that it will not face problems, problems going after here. Because just imagine you have to start from there, you have to repeat the entire process from here, right? So let us say now 6 months have passed and then they see a static timing analysis means those 6 months are lost. So you have to again go back to that. So this loop is the biggest challenge to break. So once we have done the post-layer simulations, everything is good. We do the physical verification, everything looks good. Then we do the Gerber release. Okay, so the TDS. So TDS 2 for stream is generated and it is shipped to the foundry for packing. So and the fabrication will start and then the chip comes out. Now can you go to the next? Yeah. So ATPG and DFT insertion. Okay. So as I was talking, these are some test features. Okay. So how do you make sure, or I have given something to manufacture to third party TSMC. Okay. So fabrication does not happen within the SoC. It has to. I mean, very few companies have that. Like for example, Intel, they are an in-house fab. They have their own fab. But most of the companies are fabless. So they rely on some third party like TSMC to make it better. So, I mean, how do I add, after the chip fabrication is done, how do I make sure that the chip fabrication is correct and it is matching all the requirements that was placed? So, we do something called as DFT insertion and we do something called as ATPG. ATPG is test pattern generator. Okay, so you generate some test patterns at the input and output, and you check at input it will generate some patterns and it will generate some output patterns, and it will, those patterns are verified to make sure the output is correct. Okay. Similarly, for DFT insertion, for DFT, what we do is at synthesis stage we have to enable, but this requires additional circuitry. ATPG is just you cannot do, so it has some cost associated. So you have to add some additional logic into the design, which is called design for test. Okay. So we will add some, typically we add some multiplexers. Okay. So we will create some scan chains inside the chip, and we will shift the pattern in, and we will shift it out. Okay. So there is a shift register created from using all registers in the the idea is to not verify the functionality of the design, but the idea is to verify whether the flip-flop is working correctly, whether NOT gate is working correctly, things like at a very low level. It is not the functionality of the chip. But if a flip-flop is there, does it store, does it work correctly? If it's a NOT gate, does it work correctly? That is the intention of DFT. Okay. So we will create some scan chains. Okay, and there is a shift pattern. I mean, during scan, you shift in a pattern, and you shift out that pattern as well, and you analyze that output pattern. And the ATPG test bench, ATPG vector will tell you that whether the pattern matched what the design house has given. So, when giving the chip for fabrication, we have to give the ATPG vector to them. Okay. The ATPG vector consists of input stimulus plus output, expected output stimulus. Okay, they will run this ATPG. The ATPG vector ownership remains with the design house, like not the foundry. Providing the correct ATPG vector is the job of the person who is designing the chip, not the fabrication. So he has to give you the input stimulus, he will provide output stimulus. The job of the foundry is just to force that input and observe that output. That this, whatever is the expected output, it came. Right? So that is how, and once that pattern matches, they will say, okay, this is a working chip, and they will pass it back to the fab. This, there is a delta. So let us say we make 100 chips. There might be only 97 chips that are working correctly. 3% are not, 3 chips are not working correctly. So this is called as a yield loss. So when you fabricate a chip, it is not necessary that all 100 chips will come out perfect. Right? So there is something called as a yield ratio. So sometimes we, in like any new node, for example today, the latest or the node that is in R&D, or being researched upon is the 20 angstrom, right? So we are near 20, so 2 nm, we crossed 1 nm, now we are in the angstrom. So 20 angstrom is the latest node that is in R&D, but it is not productionable. Why? Because there is a 40% yield. Meaning out of 100 chips, only 60 chips will come out correct. So this is not a feasible node today for a person who is selling chips, because he has to bear the cost of the 40 failed chips, right? So it is not, today it is not economically viable. But over a period of time they will improve that and make it to 97. And then they will say, okay, this is now economically viable, and then we will start using the 20 angstroms. Okay, so but that job is being performed at the foundry. They release, they don't release that foundry to us unless they say they have seen 97, 98. Okay, so that is the that is how we operate. And even if somebody wants to use it, they will upfront say that okay, yield is 50%. You choose whether you want to take out or not. You will have to pay us for 100 chips. Even if 50 chips are faulty, you have to pay us for that 100 chips. So it's a decision that the design house can make. That if you really need that node, I cannot work anything other than 20 angstrom, then I have to make that first. So things like that. Now, so this is in general about the whole VLSI design flow. Let us check. Yeah, we have lost 10 minutes. Okay. Yeah, so this is again the same thing that we covered. Front end and back end is segregated. Next slide. Okay, so this is formal verification. This is formal verification of a different kind. Okay, so formal verification is of two types. One is assertion-based formal verification, and one is formal verification of two netlists. Okay, so today what Aman and Sai are going to present is not this. It is assertion-based formal verification. Okay, but I will explain what this formal verification means. This formal verification means that there is an input RTL and there is an output netlist. Okay. How do you make sure that the input RTL is functionally equivalent to the RTL, to the netlist that was generated? So this is done by a formal tool. Okay. So we have a lot of tools we go over it, but basically it is a comparison of netlist to RTL. You can also do a netlist to netlist. For example, this gate level netlist and the netlist that we saw coming out of this stage, this can also be done with LEC. We call it logic equivalence check. Rather than calling it formal, I think we should refer it as logic equivalence check. So LEC is the term we normally use to do the gate level to gate level or gate level to package. Okay. So that is one check that we know. That is more important. Yeah. So this is again showing the same thing. How many types of okay. So yeah, so this is some ATAL code. I mean, how ATAL code, register transfer level code looks like. Okay. So register transfer level behavioral logic is different. So behavioral is something where it is not synthesized. Okay. So we can write variable code into forms, synthesizable as well as non-synthesizable. Then we should write. We can also write gate level code, meaning you can actually write the code in terms of instancing the AND gate or gate, but it is very it is too much to write the code in structural. Okay. Then signal assignment, and then this code should match the specification. I think this we all covered in my talk. This is just mentioning the same. Okay, now ATAL simulation. So what is functional verification? Verify the functional behavior, write the test bench to cover all required cases. What is coverage? And you write the functional verification and you collect the coverage. Coverage is nothing but it's a metric to tell you how much of the DLT, how much of the design is actually verified. For example, you might have code coverage, you might have line coverage, code coverage, you might have functional coverages. Okay, so coverage is a metric which tells you that okay, whether I have tested this particular condition, that for example in the FIFO example that we saw, let us say I want to check that full condition has been tested or not, empty condition has been tested or not. How will I know? So I will refer the coverage report and I can see that signal has been tested. Okay, so in the coverage report it will mention that this signal covered from 0 to 1 and 1 to 0. So this line is correct. Yeah, so this is the simulator that we use is Synopsys VCS. It's a basic tool. It's a simulator for simulating the test bench or RTL, and we check the waveforms. We develop some, checkers around it. That's how we check. Okay, linting, CDC, and RDC. So linting, as I said, it is checking of the grammatical mistakes. Like if you have signed, if the signal bit is not matching, then that is linting. CDC is another thing. Let's say you have two clock domains, right? Clock domain A and clock domain B. So we need to implement something called as synchronizers in between. Whenever we are crossing the signals from signal A domain to the clock domain in B, we need to implement something called as synchronizers. So why are synchronizers necessary? Can anybody say? What happens if I don't use the synchronizers? Right. So basically there will be metastability. So using synchronizers, what we ensure is that we don't hit that, that we don't get into that problem. So whenever there are two clock domains that are being, let us say, we have a design, half of it works in clock A, half of it works in clock B, then we have to implement a synchronizer stage in between. Okay, for all signals to reliably transfer over into the clock B domain, and then again back from clock B to clock A also there is a synchronizer logic. So the CDC is the clock domain crossing checks. We will tell you that okay, there is a signal crossing from clock A to clock B, but there is a missing synchronizer. Okay, so CDC is used for facts. Okay. RDC is again the same thing, it is reset learning. So basically, if you miss any synchronizer, then linking CDC will catch that problem. So by mistake, if you missed to insert a synchronizer step, then this tool will tell you that there is a series, there is a synchronizer. Okay. So yeah, we analyze CDC. Okay. Yeah, so we use spyglass, synopsis spyglass for hiding the CDC tools. CDC linking, everything is performed with spyglass. Okay, synthesis. Yes, we covered the synthesis already. So convert synthesizable constraints and tools, right? So this is, as I was saying, synopsis design compiler filter. Right, so this is the tool that we typically use. Synopsis PC topological. This is also available. Topological is more where it does some physical aware synthesis. Okay. So in the constraints that we provide to this tool, as I was saying, we define the clocks, we define the timing exceptions, we don't touch, we define what is the. So we have defined the frequency, we have defined the area, we have defined the power. Okay. So these are the constraint inputs that we do. So as I was saying, the mapping. Okay, this is a mapping of how the Verilog will look after synthesis. So this is the Verilog code, and this side is the synthesized netlist. Okay, after. Synopsis fusion compiler is also one of the DFT insertion. Yeah, so DFT insertion, as I was saying, a simple flip-flop. This simple flip-flop will be converted into something like a. So this is the scan logic or the test logic. So every D flip-flop input will be replaced by a multiplexer. There will be a multiplexer added at every input of the flip-flop. So a simple flip-flop like that will turn into flip-flop plus multiplexer process. So yeah, so why design for test? You have observability and controllability of the node. So what observability means that you should be able to observe every single node in the design. And what does controllability mean? Controllability means that every single node in the design, you should be able to control it to either set it to 0 or you set it to 1. Okay, so that is why DFT is used. So scanmux, it is, as I was saying, that is the scanmux that we have. For ATPG, we have covered ATPG already, that this is for silicon fault testing at the foundry. Right? So once I have given the design to the fabrication, he has to run this ATPG to make sure that the fabrication is correct. Okay. So this is for silicon fault testing. Then gate level simulations, this also we cover. We simulate the netlist, that is what is gate level simulations. And then we do the pre-layout testing. So DFT is the, so let us put it this way, that DFT is adding that scanmux, okay, that multiplexer adding. Now, so this is when you do DFT insertion, you are actually adding the scanmux. But when you do ATPG, you are actually toggling this input and observing this output. Silicon fault testing is nothing but, like as I was saying, whether to not gate let us say that the NOT gate, this NOT gate, so when you put a 0, you get a 1. When you put a 1, you get a 0. But let us say, in both the cases I am getting 0. Okay, so this is stuck at faulty. This means that this inverter is faulty, right? It is not giving me the design, it is stuck at ground, it is stuck at 0. Similarly, you could have a stuck at 1 fault. So these are the faults during manufacturing, something that, that gate is not working well.
So which type of the testings can be done at the designer level? We don't send it for the fabrication.
At the designer level, we do, basically, it is, see, the problem is that this NOT gate, we don't have it, right? So, we only have the netlist. The actual NOT gate will be fabricated by them, right? Using transistor. So, the transistor NOT gate will come only when the chip is fabricated. So, we can only tell them that this is a chip, let us say this is my chip. Okay. So I can only tell them that when I input a 0, I expect a 1. When I input a 1, I expect a 0. This is what I can tell them, right? Now they will run the test after making this. They need to make sure that 0 means 1, 1 means 0. This output they need to observe at their foundry. I cannot, because they are the fabrication. The chip is different.
So all these models can be tested at the fabrication level, like circuit models and everything. Boundary scanning, partial scanning.
Boundary scan is different. Boundary scan is only for the IOs, only for IO testing.
That will be the fabrication.
So see, there are boundary scan. We generate the vector at our end. So the design house doing the boundary scan at design house means performing, coming out, what is the input, what is the output. This truth table. This is nothing but stored in a format, in a file format. Okay? That which has, when I input 0, I output 1. When I 1, this is 0. So I store it in a file format. Okay, and this file I provided to them. So we don't do actually, the boundary scan has to be done. Boundary scan typically is like basically this, normally we do the boundary scan when you are placing the chip on the board. It's connectivity test. It is like connectivity test, right? So boundary scan is different, and this scan that we are talking about is different. Yeah, the DFT, it deals with each and every point, whereas boundary scan only operates at the inputs and outputs, only connection. Okay. So it is more to do with board level testing. Boundary scan is a feature that is used at board level testing, not at manufacturing capacity, not at the manufacturing facility. It is used by the board designer. So he will place the chip and then he will run boundary scan to make sure that this chip is connected with this component, this chip is also connected with this component. Boundary scan is. Okay, so does that answer your question? What is the difference between ATPG and what is? So DFT is okay. So we have Tetramax and DFT compiler. These are so Tetramax is the tool which helps us generate the ATP letter, as I said, right? It reads in the netlist, okay, and it generates this truth table 0, 1, 1, 0. Okay. So if let us say if my chip is just a NOT gate, the Tetramax will generate a file with just this. Only this much content. Example, I'm saying. Okay. So it will only generate, Tetamax will generate this 0, 1, 1, 0. Okay, and this file, which we call as the vector file, this has to go to the one. DFT compiler is the one which is performing this multiplexer addition. Yeah. Scan. Okay, so there are some additional videos for your information if you want to use it. And I think next slide. Questions, if any? Please feel free to reach us.
Sir, it would be good if you can show it on your laptop, the design tool that you explained theoretically. We want to see it. How synopsis tool is done.
So actually, we are not allowed to do that. I mean, we cannot. Yeah, but that has some challenges. So we are working with. So the idea is to have a license tools access. Yeah. So that is how we. I mean, we are also working with Chital to get that MOU side, but it has some so that you will have access to those licenses and we can also try out those things that we can have detailed sessions hands-on. So the hands-on session is not that fun. Yes. But that is a totally different flow. I mean, that is an analog and mixing signal. So that is for analog design. This what we are covering today is digital. For analog design, there is a totally different flow.
Sir, can we have discussion on code coverage once again?
Yeah, sure. So code coverage is nothing but if I have a if statement, okay, so has the if part been covered, the else part. Okay, so I need to simulate code. So basically code coverage will give me an indication that whether or not if only let us say I have this multiplex. If I have written so let us say I have this if let's say right now is equal to 1, we know x sign else something like this. Let us say this is my code. Now the code coverage will tell you that this statement is this part is covered, but this is not covered.
In simulation.
In simulation.
In simulation.
Yeah.
And
So when you have simulated, what it means is you have only tested for condition when this signal is 1. You have not tested for write enable equal to 0. So your test needs to be enhanced to cover this condition.
so synopsis do give us code coverage. So in that case, do synopsis tool itself generate the test vectors, or we are going to give the test vectors and the tool will tell us that this is the code coverage for whatever test vectors you have generated.
Right. So we don't provide the test vectors. Test vector, the person, the test bench team normally writes the test.
Okay.
So you have to enhance your test, you have to update your test and add another test for like you have done for write enable equal to 1. You will add another test So let us say this is test 1 and this is test 0. Okay, so you will test both conditions and then it will say, okay, you have verified this as well as this.
Sir, and when we say code coverage line by line or block, it may be something that line is covered or that particular block is covered. Is it something like this?
Block, line coverage, I'm aware of line coverage, I'm aware of block. Conditional coverage is there.
Okay.
So,
Might be my mistake, sir.
In your PPT, I mentioned that code coverage instead of that line and block coverage is also block coverage is also there. So let's say it's any other block which is having some functionality based on a specific feature that contains multiple expressions or multiple features in a single block. So that explains but it's a very minute use of block coverage. Usually we check expression coverage and collector coverage. But there is a part of it's code coverage itself. So if you have defined modules which have block names and you want to cover that particular blocks, in that case you can have separate flags which will enable that block coverage for that specific block. So it is part of a code coverage itself.
Okay. So it's like a testing part.
Yes, it's a testing part.
आप कितना सा block check करना चाहते हो या
exactly.
पूरा code cover
Yes, exactly.
Okay.
Okay, thank you. It was nice.
And I'll discuss some of the topics related to verification on design verification flow of VLSI. So as Anjan mentioned, we are just going to focus on front-end verification, not the back-end one. So we'll focus on functional verification and formal verification for the chip for SC. My domain is major on functional verification, so it involves code coverage, test development, architecture of verification development, planning. All those areas I have been working since 5 years. Aman and Sai will continue with formal verification of the session. So today's main topics will be focusing on what is verification, vision and goal of verification. So as a verification engineer, what should be your vision and how you will convert that vision into the goal? What should be taken care in the process of complete takeout as a verification engineer? Then what is the importance of verification in the whole cycle of developing a chip? Verification environment. To verify a chip, we require environment, we require methodology, we require tool, we require infrastructure. All those information will be covered in verification environment. And verification planning, execution for strategy, how we will execute what we have planned. So that will be the main focus of this session today. So can you tell me what is verification in a plain language? Why do we require verification? What is the purpose of verification? Yes, that is one of the main goals. But the main goal is for verification. What is exactly verification? Is we have some vision to implement. The designer implements that particular vision. We need to make sure that implementation that we have done, the coding we have done, that should match the vision of the product. So what verification engineer do is it checks the correctness of the implementation. So whatever the code has been made, that should be aligned with the specification or vision that we have, the planning we have. So as a verification as a whole, it focuses on the correctness of the design or what we have coded. So that is the main thing. So, as I said, verification is a component which includes infrastructure, methodology, product understanding, and monitoring. What is monitoring? So, once we have created a verification structure, we need to make it updated. We need to monitor. We need to check frequently whether it's aligned with the changes of the design. Is it updated with the design changes? Is it required to be changed? So that all things are considered, or it's a part of the verification process. What is infrastructure or methodology? So infrastructure and methodology is also part of the verification planning. So when we start verifying a design, which has been coded by designer, we need to focus how we will verify it. We need to check what methodology will be used. If it's a small block, we can check using Verilog language. If it's a huge specification, standard specification, we require more advanced technology to verify those things. So for that, what we require is to finalize one approach to verify specific product. There are a lot of advanced technology that has been used for verification, like system Verilog is there, UVM is there. Right now, UVM is the topmost or advanced technology that we use for verifying products in the industry. And a lot of industry standards are aligned with, or tools are aligned with the UVM methodology. So the methodology is part of verification. Then product understanding. So product understanding is a very generic version of verification. Like designers have some specific vision for product understanding. Verification engineer needs a different approach to complete the verification for that particular implementation that designer has done. So what we have to do is we have to separately have a point of view or understanding with the designer to completely verify product in a different way. I mean, we cannot take designer's perspective and complete the verification process. We have to have our own opinion or understanding according to the specification that has been provided for the product. So that is also part of a verification. Okay, so what is important? So what is the challenge when we work with a verification engineer? Okay, so we are advancing in the technology. We are moving from small block to IPs to SOCs. Now processors are involved, AIs are involved. So it is getting challenging to verify all the individual products and to reuse that particular infrastructure that we are following for IP to SOC to AIs. So those all things needs to be aligned, and that needs to be planned ahead of a project start. Because what happens once you start, as Anjan mentioned, it's a 5-year process. It's not just a year process or 5-month process. So we have to plan ahead, and we have to consider the advanced technology that will be implemented 5 years after we started planning. So that needs to be all considered when we are starting verification planning. And verification planning is the major or the challenging part of the verification whole cycle, because what we are going to verify, how we are going to verify, what needs to be included, how we can say that verification is complete. That is one of the things that needs to be considered when we are planning. So can anyone tell me that how we can say that verification is done or verification is complete? Just functional coverage. So that comes to individual product, and that comes to the team that is involved. So verification, it's very complex or challenging thing to complete. The goal or ideal thing to complete a verification is to collect 100% of code coverage and 100% of functional coverage. Not only functional coverage, but code coverage needs to be 100% also, because code coverage focus on the optimized way of coding. It focuses on your design activity, that how much you have optimized or clearly developed your design product. So not only functional coverage, but code coverage also helps to improve our product. There are few cases where code coverage implies that some scenarios has been missing. So that needs to be analyzed, and that needs to be covered as well in order to have a complete verification verification on a product. So that is challenging. Right now, industry is focusing on design and verification on both areas. As I mentioned, that verification needs to have a different perspective than design. Designer can also verify the product, but the problem is the person who has designed, they have a particular vision to create that particular product. So there are chances that they have misunderstood, they have different opinion on certain features, they have completely they have differently generated some code which might not be optimized. There are a lot of things that needs to be checked on different person's perspective, and for that verification team is required. So verification is not just a verification in team's role that requires to be completed. We do have sessions with designers, we do have sessions with architects, design engineers, all other tools, developers, software engineers. We involve them and we create a verification plan in order to complete a verification cycle. So each things that I mentioned that have their own challenges. So it's not easy that verification is just to collect coverage or just to collect code coverage to 100% and we can say that the product is complete. The product needs to be that much, we should have that much confidence that the product is complete. At that point we can say that the product is reliable and we can release that product. So that is the goal of the verification engineer, to have efficient plan and then execute that plan according to the reviews, sessions, combined effort and complete the verification cycle. Okay, so this is one of the case where we can say that whether the design is accurate or not. You can see that there are four components that mentions that whether the design is bad or whether the good design is there. If it's failing or if it's passing in the simulation run. So what we can say is there are two types of failures we can analyze by running the simulation. What is a good design? If we are catching some false specification related feature which is failing, but it's a false failing, like it should not be failed. We have implemented correctly in design, but it's failing. Still, it's failing. So in that case, there could be some reasons like software is not aligned with the design. VIPs. VIP is a verification IP. We usually use verification IP to reduce our efforts. VIP is test bench component that we use. It's a functional model which mimics the actual DUT. And it helps us to speed up the process of verification. As I said, designers should not have a verification point of view. So what happens if we are running design in a master mode? We can run in the same as a slave mode, but we should not do that because we need to verify master mode is completely working fine. What if we have aligned the design or the VIP according to the master mode and not according to the specification? In that case, it will show that the test is passing, but it's not passing actually because it's design oriented, not specification oriented. So what we do is we integrate a verification IP which has predefined VFMs. VFMs are first functional models. So it has a driver logic. It has some specific logic which mimics the driving or monitoring part of the test bench. So we use that VFMs, VIPs, and we check. So in those cases, there could be chances that VIP is not behaving correctly. Design is correct, it is as specification. So that will show that your test case is passing, but not due to design, but other elements that we are using. So that could be considered as a good design because we need to fix according to the design our environment. But what is scary or what is important or what should be focused on is the false positive. So what happens is in some cases like coverage default values, those values if you are creating coverage on specific values or on specific scenarios, default values are by default covered. When you run simulation, default values object is collected and it collects the coverage. And now in some scenarios we are not running that specific scenario. We have cover points, we have cover groups developed on that, but we are not running test case to cover that particular coverage. So in that case, we can say that it's a false coverage. It's collecting default value, which is not intended to cover in the scenario coverage. So those sort of things we need to analyze by the coverage or by debugging also we need to analyze those things we need to focus on specification that this scenario needs to be generated in order to complete the verification. So in this particular things, we might have missed some of the actual scenarios that not has been verified properly. So that is a scary part, and that should not be the case. And those minute details are all dependent on verification planning. We need to plan, analyze, execute. This three process we need to have consistent as a verification engineer in order to have a complete verification cycle. Okay, so next topic is validation versus verification. So can you tell me what is validation? What is validation? It's the same as verification, right? Verification is also proving. So what is the difference between validation and verification?
Whatever the mathematical modeling is, mathematical output we are expecting the same thing we are validating.
So what according to my understanding, what is that? Validation is depending on the requirements that has been finalized and features that has been confirmed. That this feature, according to this specification, these are the requirements. So what we are doing is we are validating that this particular requirements has been met according to the coverage metrics, functional coverage, and all those things. But in verification, we are not verifying or validating that requirements are met or not. We are checking the functionality of that requirements. So basic difference between validation and verification is when we are verifying, we are focusing on functionality, not on the requirements according to the specification or planning according to the planning. So that is the basic difference between validation and verification. So if you can see these two phrases, it will explain that what is the difference between the validation and verification. Right product according to the specification, that is the validation, and product is right, which means you are verifying the intention of the product, and that is the right. Okay, so this is the this is the model that we follow for verification and validation. On the top of any planning or any verification start, what we do is we create a requirements for the specific product and test suits or requirement related tests that needs to be executed, scenario generations, all those things according to the requirement that needs to be created. It is called test planning. So test planning is required. That is considered or part of a validation process, or that is the topmost or the first step that we do. According to the test planning and requirements, what we do is we divide the IP into sub-blocks or feature-wise. We distribute that features. We distribute the specification into specific categories: data corruption, error injections, data path cleanup, status read. Those some of the features which product needs to have in order to have a functionality complete. Those things are categorized furthermore into verification planning. So those have different specification. Let's say CRC. CRC needs to have specific scenarios that needs to be corrected, checked. Then error injection is there. Error injection needs to have a proper recovery mechanism, or those areas are there. So those will have different specification regarding the features or subcomponents. So that needs to be covered also while we are planning and while we are verifying those things. And the base needs to be our code. DOT is design under test. So whatever we are building on the DOT. Here what happens is in design view, we micro analyze design. But for verification, what we do is for verification engineer, this is black box. We don't consider or check unless we are debugging into deep. We don't check code of a design. What we do is our scope is out of design. So let's say this is the design. What we are doing is we focus on inputs, we focus on outputs. our focus is more on those areas and on functionality, that what we are providing as an input that needs to be matched with the outputs. The complete history is black box for us. So for a verification engineer, perspective of the design code is different than the designer itself. Okay, so let's say, as I mentioned earlier, that as a verification engineer, we first have to build a vision, and then we have to achieve that vision that we have. So there are components which come or which are categorized as a vision. So first thing is team development. As I mentioned, the verification process is not simple process. It requires efforts. As we are advancing in the technology, we require separate test benches. We require more advanced features like as we have object-oriented programming, reusability is there. Needs to be robust. It can be used in multiple projects. Those sort of features require more effort to build any specific environment. For that, we require a specific team, and that is the first step that it starts the verification planning and team build-up. It's a first step of vision. After that, what we do is we create an environment. Now, for Verilog, the environment creation is completely different than system Verilog or UVM. Verilog is more focused for designer perspectives, test bench development than verification perspective, because as I mentioned, as we advance into technology, there are a lot of features, a lot of efficient ways that have been involved in the technology that we can use in order to have efficient products. Object-oriented programming, randomization, coverage collection, those features are not there in Verilog. There are some randomizations, but it's not as a mark that we require for the verifying any specific products. So that is part of a generic environment buildup that we require. And the third part is automation. Now, what is automation? So automation is also part of verification. Automation is a verification engineer's guide. We need to have automation clarity very much, because what happens is we usually do redundant tasks. To reduce the effort doing redundant tasks, we involve automation. If you do not involve automation, manual work increases, and that is not efficient to complete the cycle in dedicated timeline that we have. So every product have automation flow ready or needs to be built according to the requirement of the product. Majority automation have logs cleanup, logs collection, regression runs. What is regression? So regression is part of verification. When we involve randomization into test bench, one test will cover just 50% of the functionality, or let's say 50% of code coverage is covered. Now what we have to do is randomization. When we run one test case, it's targeting to specific area only. We need to run that multiple times in order to cover the whole metrics that we have developed. So regression is nothing but to repeating that particular test case in a multiple counts, so that we can collect and merge the coverage that we have. So we collect the data in multiple runs in a one go, and that in that way we can have all the data that is required to complete the verification. So that is the regression. For that we have different flows. It should be aligned with there are a lot of things that needs. It should be aligned with the tool. It should be aligned with the scripting that we can use to filter out data. We have multiple errors. Let's say we run with 100 counts. We have 10 errors. There is not efficient way to check all the folders and all the test log to filter out specific errors. So what we can do is we can create one script which will filter out. Perl script could be there, Python script could be there. We can filter out errors from that all folders and create one final report which will just focus on errors. So we can just focus on debugging those errors instead of doing manual work going through all the folders and files. So those all things, cleanup, collection of errors, report generation, tools needs to be enabled for specific features. Those all things comes into part of automation, and that is a very important part to have a smooth takeout for any product. And the goal part is to execute whatever we have in a vision, in a planning. That is our goal. To collect. So first of all, what we need to do is our main goal is to have as less bugs as we can have into a product. So we have to focus on RTL, the golden reference model. What is golden reference model? So golden reference model is mimicking the RTL. It's not exact RTL. It's mimicking RTL according to the specification that we can compare with actual behavior. So golden reference model is specification oriented. It's not implementation oriented. Implementation oriented outputs will be created by simulation runs, and we will compare it with the golden reference that we have. So we have to focus on golden reference. It needs to be thoroughly reviewed with lot of engineers. Always review sessions are there, which will have discussions on according to the specification what should be there in the golden reference model, what can be eliminated, what can be used in a different way. Those things needs to be completed in that planning. So golden reference model is our goal that needs to be efficient and optimized in a way that we collect whatever we are comparing the data, we can rely on that model. Okay, so next step is coverage. As I'm talking about coverage a lot, verification engineers' main focus is on coverage. What is coverage? So when we are enabling randomization, there should be a matrix that needs to collect all the information. We can randomize anything, but there should be a matrix that will specify that according to my product or according to my requirement, I have collected what I need. So coverage matrix is basically that part that verification engineer developed to make sure that whatever the product is required to have covered, it should be there into that coverage matrix. There are two types of coverage, functional coverage and code coverage. We'll check more in detail for that. Okay, so tape outs, reduce number of tape outs. That is the scary one. What happens is we need to have a tape out according to market timeline. If we are not aligned with the market timeline, there is no point of having a tape out itself. So planning and goal execution needs to be aligned with the timeline according to the business plan and according to the actual environment that we are in. I mean, the actual industry that we are in. According to that, we have to plan out our tapeouts, and to have that, we have to reduce our tapeout counts. We can have as much as, initially we can have multiple tapeouts, but the final tapeout should be as low as we could have. Actually, it should not have multiple tapeouts in the final tapeout, because it relies on business finance, on client finance, and then on our reputation. All other metrics are involved in those areas. So we have to have that goal that we are reducing the tape out, or we are taking out according to the timelines that we are having for deliveries. So verification strategy. Verification strategy have multiple things that involves. Planning, as I'm discussing about. Next is the verification environment development. So we have to finalize what environment will create methodology, what specific components are required in order to verify a product. Those needs to be finalized when we are finalizing an environment development. So as an architect, for designer, there is a role of architect which finalize which interface will be required, which modules will be required, what functionality will be implemented. Same as for verification engineer, environment developers are there. So for them, it needs to be finalized what we are going to use. Are we going to use VITs? Are we going to use this interfaces? How can we minimize the code that we are writing to make it more optimized. We need to make reusable architecture as master and slave that I'm talking about. If you can reuse master component as a slave, we need to think according to that perspective, that we have to finalize that some code can be reused and we are going to reuse that in a particular manner. So that comes into verification environment planning, and we need to finalize if we are using this interfaces. According to that, monitors will be there, agents will be there. This component will be used for multiple agents or multiple interfaces. Those needs to be finalized when we are finalizing environment architecture. Assertions. Assertions are part of verification actually. So assertions, let's say we have signal level interaction between two modules. All information cannot be verified on environment level. Some information needs to be verified prior to environment level. Data integrity checks. What if the handshake between the two modules has not been happened properly and we collected data? Data is corrupted, but handshake is itself buggy. So we are wasting time to collect the data and comparing, and lot of runtime is there, lot of issues we will face while we are doing this process. So what happens is assertions are the essential part in this such scenarios where interface level activities can be measured and checked in order to have advanced clarity on specific data integrity checks or specific features that we are going to verify. So assertions are integral part of verification, and we have separate session on formal verification. They use assertions intensively for formal development. Next is constraint randomization or constraint driven verification. So constraint driven verification came into picture when system Verilog was introduced. System Verilog is advanced technology than Verilog. So when we are adding randomization or object-oriented programming, what happens is we need to limit our stimulation. I mean, let's say we have a memory module. Our address line is 2:n. And we want to cover the data, the address line is there, and we want to cover that address line only. So 2:n entries will be there. Now, out of that 2:n entries, whatever we are generating, we are using variable which has, let's say, 32-bit. But the address line is just 2:3, let's say 8. So what about after that? The randomization will create the values after that also. But those are not required for us because those are invalid address lines which will not be covered at all. So that is again a false coverage that we don't need or we don't require. It will be covered because we have generated it, but it will be false coverage because we have not implemented that, and that is not required. So controlling our inputs or controlling our stimulus is required when randomization is involved. So in that case, what we do is, there is a construct called constraint. We use that construct and we limit the randomization. So and this sort of verification is constraint verification, which is involved in system Verilog and UVM itself. Okay, so API is one of the another feature that we have in system Verilog for UVM. APIs are nothing but functions that we build, and we can reuse that function all over the test bench. I mean, we can reuse anywhere, whichever hierarchy level we want to use, we can use that. So I'll show you a simple example for APIs. Let's say we have register space. We want to write data and collect data from that. Now, in Verilog, what we have to do is we have to write a code which will specify that address line is this and collect the data on this particular line. For system Verilog, what we do is we create an interface. We have a variable which will point to the address and data. And in test, what we'll do is we create two functions, write function and read function, and make those two functions generic, which will have arguments, address and data. So address and data are what it's generic variable. So wherever we want to write or wherever we want to read, what we can do is we call this function specifically for write at any address at any data collection. We can do that, and for this sort of functionalities or this sort of features, what we do is we create a generic APIs and we use across the test bench itself. Use revision control regression. Okay, so this is one of the part of automation. So are you guys familiar with revision control? Okay, so when we are working in a team of let's say 50 people, we are modifying code every day. I am doing something on the same file. She is doing something. You are doing something. So we need to have consistency in the code when we are multiple people are modifying the same code. Or else there will be coherency, there will be data missing, there will be incorrect data, corruption data on the code. It will be there. So what we do is we in the industry we use revision control. There are a lot of revision control tools that provide this facility. In that what we do, we check out the code. We have local copy in our area. We work on that area. We submit that code. When we are submitting, we check whether someone else has been worked on those area or not. Is there any conflict on those code or not? Those things needs to be checked prior to submitting our changes. So that is the revision control. It's a tool basically, and it has GUIs, it has command lines. We can use commands, and it's maintaining the code across the team. That's what it is doing. So that needs to be finalized. That needs to be have proper implementation done. Every engineer should have knowledge of that, because if you are not using it properly, then only it will corrupt the data, which is not the case that we want. So that is there. Regression, bug tracking. Bug tracking is one of the other feature that is required as a verification engineer or design engineer. We are fixing something. We are recognizing issues, but there should be a data management for that particular bugs. In order to have information that what we have verified, and those bugs needs to be tracked somewhere. So there are tools which help us to track or manage this particular issue bugs, and we use in the industry those sort of tools. Jira is one of them, and if you have heard about it. So those tracking mechanisms are required in order to have old data. Let's say after 5 years I am facing the same issue and I already have fixed that issue. I should have information on those issues that I have worked. So we have, there are tracker IDs and all those things are there. So we have to go back to that tracker ID and to check. We can analyze and fix again those issues. So that is also part of one of the verification planning or verification execution that we require to have in place. The next is completely based on infrastructure and project requirement. So LSF is one of the mechanism which uses load sharing facility of the terminal. So when you are using terminal, if you are running regression, let's say, and you are working also, regression takes a lot of load when we are running it, because it has long jobs, it has a lot of memory that is being used, processors are occupied for that regressions and all those things. At that point of time, we required some mechanism to control that load and to control the overloading our system. So LSF is one of that systems that we use in order to manage the load distribution across the operating system or the server. So that has been used for all industry standards use this particular system, and that is required to be implemented in such a way that we don't have memory issues, we don't have server issues. If these things are not properly implemented or not has been planned out well-equipped or planned out properly, it may delay our process of debugging or actual work. So this has to be in place. Okay, so these are the so in system Verilog or in UVM, the test bench is divided in sub layers. So there is a layered structure that follows in the test bench for system Verilog. It's completely different than Verilog. So the basic or the base layer which directly interacts with DUT is the signal layer. So we have ports, we have signals, input signal, output signals, which are directly connected to DUT. Now, system Verilog introduced interface. Interface is a variable which can be generically used for multiple signals in multiple scenarios, like for input or for output. It can be used in such a way that one variable can access multiple signals. So that is part of a very basic signal layer of the test bench architecture. Then on the top of that we have command layer. Command layer is categorizing into the components that we are going to use. Those components will be agent, VFNs, drivers, which will directly interact with the interface layer. So those are the part of the command layer, protocol layer, which will use or which will drive a specific stimulus to the interface or signal level. On the top of that, we have functional layer. Now, this is getting abstract. When we move ahead, it gets abstract. So what we have on the functional layer is sequences. On driver layer, we are just driving some data, but in which order we are going to drive, or what specific sequence we are going to drive in, like we are driving in read, write, read, or what specific scenario we want to generate, that comes into the functional layer of the test bench architecture. And scenario level is the most abstract level that is part of the planning instead of just test bench architecture. So in that, there are multiple sequences that we can use, like back-to-back read, write, we want. In that case, we define a scenario which will have multiple sequences, read, write sequences, and we can execute it in a single test bench. So that all comes into planning of test bench architecture and environment. We code this according to the language that we are using, if it is SV or UPM. So this is the typical structure of Verilog test bench. So what we have is DUT, design under test. We have VFMs. These VFMs are nothing but the driver or monitors which will drive some data from the stimulus that we are generating onto the DUT, or collect the data, output data for the specific stimulus. And what we are doing is, as I mentioned, the reference model is the model in which we will mimic the DUT functionality. So what we are doing is, what we are driving, that will collect, and what will be the output of the driven stimulus that will be collected in the reference model. That will be the actual check. Output will be the check. For the checker, output will be the actual data, and that will be compared with the reference model data. And in that way, we can finalize that this test piece is passing clearly, or other checkers can be involved in that. So moving from the Verilog test bench to the constraint-driven test bench, there is a huge difference. First, we are moving from Verilog to system Verilog. System Verilog will involve dynamic structures of class, object-oriented concepts are there. So what object-oriented concepts do is, it shares data across the different concepts, different objects. We create a template as a class. We create objects of that template, and we reuse it according to the use that we require in multiple ways. In multiple scenarios, the object will be different from the one which have created for different scenarios. So reusability is increased while we are using this particular template when we are creating an object. So in that case, we require different structure that we traditionally was following for Verilog structure. So in this particular structure, you can see okay. So in this particular structure, we have components such as DUT is the common one. We have monitors, and the input monitors are there. These are the drivers. We can say that it's a drivers. It's all class based, so it's all template, and we manipulate that template using objects. So those are part of the test bench, and scoreboard is nothing but the checkers that we use to compare the data. So what we are doing is input monitor, what we are driving that will be sent to the checker in the scoreboard. Scoreboard is what it is doing is it's creating a scope for verifying checkers or multiple information that will be scoped in a single scope. Let's say coverage is one of that scope that is required to be checked with the checkers. So it's narrowing the or categorizing the final result that we require in order to have verification coverage. So that's what scoreboard is doing here. So it will check the input and output and say whether the test is passed or failed. In this particular test-bench architecture, what has been changed is this part. So what is the difference between directed test and random generated test? So when we are randomizing, as I said, we can add constraint, but and we can narrow down or limit the randomization. But there is one more thing that is tool dependent, which is randomization. If you are running regression, there could be a possibility that all count will have same randomization. So there could be the chance that some configurations or some scenario had not been created or not been covered into the simulation run, even in the regression. So for that specific scenarios, what we need to do is we need to create a directed test case and we need to cover that into our coverage. So directed code coverage is coded test is nothing but we manipulate the constraints. We check the stimulus and we create the stimulus according to the missing part that we did not cover in the regression, and we run that particular test. So that is one of the major change from Verilog to system Verilog that we have. And this all components are reusable components. Some components can be used in a multiple way. I can say that we had that example of master and slave. So let's say we have a driver, we have configuration to enable that driver. What we can do is we can change the configuration, we can use that driver as a master, we can use that driver, particular same driver, because we have template. We are using that as a slave. So reusability is increased by defining the same code in a different way. So that has been evolved from Verilog to system Verilog. So what is the cycle, actual verification cycle when we are involving coverage and when we are verifying the full takeout cycle on the perspective of verification planning. So what happens is initially we run test cases of regression on pure random scenarios. So pure random scenario will increase the verification goals or coverage data significantly, because it will have multiple things randomized and we have multiple coverage means that will be hit for particular scenarios. So we start with the pure random scenarios. Then we need to limit the randomization. As I mentioned, constraints needs to be added to limit illegal stimulus or the stimulus which are not required. So what we do is we add constraint in order to dilute the randomization that was being created. Unnecessary randomization and coverage that was not required, we remove that by adding coverage constraints and we limit that. So it will improve significantly again on the takeout cycle for the coverage. Now this is the difficult part, because what happens here is we have to analyze each and every cover properties, each and every coverage in order to find the particular holes in the coverage database or in verification. We need to find scenarios which are not covered due to randomization, due to other issues. We have to finalize that and we have to create a directed test for that. So that is the complete cycle for verification that we follow. First pure random, then constraint, and then directed one. Actually, I already told about this. What is the difference between Verilog test bench and object-oriented test bench? So first is the reusability that we enable. The second is Verilog is very designer friendly. So if designer wants to just verify specific module in specific order. So they have their personal test bench which can focus on that particular feature. No more than 5 minutes or 10 minutes, I would say, required in order to for a small block to verify or to create a test bench for specific feature completion. I mean, they can do effort is less to create a very long test bench compared to the full-blown verification test bench. So if we don't have specific features or test cases ready for that, while designer is designing specific module, that means they can have their own very long test bench and target to that particular feature and verify it prior to verification process. So that is the purpose that we can use very long. But in object-oriented or in SV,
the first would be, if we turn on the switch, the bulb must glow. This is an example of assertion. Like we are checking the behavior of a bulb is working correctly or not. So if we turn, the requirement is, if we turn on the switch, the bulb must glow. If this assertion fails, if we turn on the switch and bulb doesn't glow, we can say that the design has bugs. We need to fix it. But then comes the second statement, power supply should be present. This is an example of constraint. The above assertion will fail in absence of power supply. Let's suppose we don't have any power supply and if we turn on the switch, the bulb won't glow. The design might be right, but it won't glow because there is no power supply. That would be a false negative. So we require these constraints in order for the bulb to glow. We can have the statement 3. Will the bulb glow in absence of power supply? This is something we are interested to see. We can write a cover to figure it out. Cover can be proven or falsified, but whereas assertions, that should be always be true. Else we can say the design has bugs. Any questions on this? So, the basics of properties. Yeah, then we will have a simple handshake protocol and we are going to verify this and Aman going to explain this example.
So thank you Sai for explaining what is FPV and what are properties and what are different types of properties. So now we will understand why we need properties and how it is used in formal verification with a simple example. So first we will see a small design. We will understand what is a design with a simple protocol, and then we will see how we are going to verify the design using formal and why we need properties in formal verification. Understanding the design. So this is our simple DOT. It has 3 interfaces. All of the 3 interfaces have 3 signals: reg, done, and busy. So now I will explain you how this interface works, and then we will go in detail about the protocol. So it's like this is the main int, which first request. This request is sent to int1 and int2. When we send the request, it's like the interface gets busy. So after sending the request, busy get asserted. Now, once we have sent the request and busy is high, it shows that interface is waiting for done. Correct? So once we get a done, the busy get deasserted for all the 3 interfaces. So it's like request indicates a new request and it's a pulse signal. It can be asserted when interface is not busy. We all know that if the interface is busy, we can't send a new request. Then we have done. Done is used to indicate that our request is completed, and it can be only asserted when an interface is busy. Meaning we got a request, interface is busy, and now it's waiting for done. Then busy is used to indicate that interface is busy or not busy. Sorry for that. So busy should be asserted after the request is sent, and it will get deasserted after we get the done. Understood what is the interface and how reg, done, and busy are there? Okay. We'll move to the protocol. So here what I'm doing is I'm trying to explain reg, done, busy with a simple waveform. So we will consider the requester and the responder. So the requester is going to request the responder, and then we will get the request as high. Once the request is high, as I told you, the interface gets busy. So busy will get high until we get the done. Once we get the done, the request done act completed and the busy will get low. Similarly, 2 and 3 are indicating how early we can get the reg done handshake. So we can get rec done handshake in next cycle also. Or after we get rec done handshake, we can send a new request as soon as we get that done. So it's like once the busy is low, you can send a new request, and once once you send a request, we should wait for the done. Now we will see how this rec done busy is used in RDUT. So as I explained, RDUT has 3 interfaces, all are based on rec done busy protocol. So let's see. So after the reset, the int, the purple one, has sent a request. After sending the request, its busy get high, and the request is transferred to int1 and int2. That's indicated by yellow and green color. After getting the request, int1 and int2 will also assert their busy signal. And here we see that done is not sent for any of the signal. Therefore, the main done is not asserted yet. In the next cycle, the green interface got done. But still, this done is not high because we said that main done will get high only when both of the done of green and yellow are asserted. So it's still waiting for the done of yellow. And once we get done of yellow, we will assert the main done. And as I said, after getting the done, the busy signal will go low. So this is the interface protocol for this our design. Again, I am explaining one more scenario. In this, you can forward. Yeah. It's not always like the green request will get done first. It's also possible that done for the yellow request will come before the green. So this is just another scenario where I am showing that both of the interfaces can get done independent of each other, and one can come before and one can come after. And this is the third scenario which indicates that the earliest possible time of getting done. It's as you send the request, in the next cycle you got the done for both yellow and green interface, and then our main done gets high. So any question in this protocol? Right? No, you understood the protocol? Good. So now we'll see how we can verify this protocol through our formal verification technique. So as I mentioned, to verify design in formal, we use property. So now let's see how we write a property. So I will use the same rec done protocol, and I will explain how we write a property. So what is a property? Anybody have wrote assertions before, or have any idea what is assertions, how we write properties and all? No? Okay. So as I mentioned, property like formal is a search engine, right? He told us. So in Google we use what we type in English, right, to search for answers. So in formal you have to write a property to search for answers. So property is used by formal to search something. So how we write a property and what is a property? Property is just a Boolean expression which tells what design requirements are, or it's a relationship between the two signals. So as you can see, the same protocol, once you get a request, busy gets high. So we will write a property for this scenario. Once you get a request, busy is getting high. So how you write a property? First, name of the property. It can be anything like you want. You can simply write rec next busy. But we write meaningful names because it's easy for one person to understand that what property is doing. Okay. Then we write type of property. As I said, there are 3 types of property: assume, assert, and cover. But we are writing in assert property. I will explain different types of property in future slides. Okay. Then we write when we have to check this scenario. Correct? When we have to check at every clock edge. Therefore, we write at passage of every clock, and we will not check if it's in the reset state. And then what is the actual property? What this property says? Once you get a rec, in next cycle you get a busy. So this property check if you get a request. In next cycle you will check for busy. Any question in property syntax?
Do you understand the operator? There is a or, yeah, or and then so maybe
Yeah, I can write, but it's there, right? Okay. Let me see there. Okay. So what that operator is like this one, right? Okay. So it means if your something is getting triggered here is this cycle. I will remember is 1, 2, 3. So if you want to check in next cycle, you will use this operator. So it will get triggered here, but it will check in cycle number 3. But if you use this operator, which is single line, it will check in the same cycle at this point. So this operator means check in same cycle, and if you have equal to, it means check in the next cycle. Any other questions? Next, no? So now we will see different types of property, assertions, assumptions, and cover, and then we will some. So assertions. So I told you there are 3 types of property, and property are used by format to check something. But now we'll see what are assertions. So here is a simple example. If you ask Google to search a smartphone with 3 cameras, it will search its database and give you result. Okay. So now you can see here are different phone companies having different prices for each of the phones which have 3 cameras. But in same way, you can ask format to find your trace in which you check the output is behaving as expected or not. Okay. So formal will go to his design space, which I explained, like we have 2 raised to m inputs and states. So to produce the design state of 2 raised to m plus n combination, correct? So our formal will explore this complete design state, and it will check if your output is behaving as expected or not. And it will show you trace or in trace, I mean it will show you a waveform if it is behaving as expected or not. So but in our DUT we have both inputs and outputs, correct? So where you are going to write assertions? So any idea? I don't see this. So like where you write assertions, on input or output? It's written at least. Yeah. So why we write on output?
To check the expected.
Correct. So we write so assertion is something which should be always true. So output therefore should be always true. Therefore assertion is written on output. Okay. So we will write a property for our DUT where we will check the behavior of our output signals. So in our DUT we have done, busy, rec1 and rec2 as output signals. So we will write a property to check their behavior. So from our DUT we know that the done should be only high when we have a busy. Correct? Correct. So we will write a property for it, like the name of the property. It's an assert property. It depends upon the clock, and it should be disable if there is a reset. And what we are checking? We are checking that done should be high when busy is there in the same cycle. We are not checking that if your busy is high, it should be in the next cycle. In the same cycle, when we get done, busy should be high. So this is that operator which checks in the same cycle. Okay. So after we we write this property and we run formal. So formal is going to show you a trace where this property failed, because formal is used to check the behavior of the design, correct? We wrote that done should be high when busy is high, but you can see in waveform we got done, but busy is low. So this is not correct. Oh, yeah, there is something else wrong in this waveform. Can someone tell me? If you understood the protocol and correct. So here we are getting done without sending a request, which is also not correct. We should first send a request, then we should get a done, right? Understood? Yes. Yeah. Right. So let's see why this done got asserted. We will add all the signals in the formal to check what happened. So as you can see here, the rec1 is also not there, rec2 is also not there, but we are getting done 1 and done 2. So done 1 and done 2 are our inputs to our DUT. So we need to control our inputs. So how we are going to control our inputs? Any idea? Because as I said, in formal we don't provide inputs to our test bench. But we are seeing that here inputs are not behaving as we expected. Then how we are going to control our inputs? Constraints. Correct. So we are going to write constraints. So in simulation there is a test bench which drives the input. But in formal we use the assumptions or constraints to control our input signals. So now let's see what are assumptions or constraints. Okay, so here is example. I can say assumptions are simply like a filter. So if you want to search for a phone, I said it's a smartphone with 3 cameras, but now you want to filter it for a price range. So you will say Google smartphone with 3 cameras under 15,000. It will search its database and it will show you different companies providing smartphones with 3 cameras under 15,000. Similarly, you can ask Formal to search or to check if the output is working as expected with legal inputs. So constraint is used to So constraints or assumption, they are used interchangeably. So please don't get confused between assumption or constraint. They both are same. So constraints or assumption are used to restrict the behavior of our design inputs to prevent them from taking illegal values. As Meeti explained that we have an address bus which is 2�3, so it has 8 possible values, correct? But it's possible that not all the 8 possible values are legal values. So we need to constrain that to some specific values, correct? May I give you some different example? You guys understood?
Yes.
Great. So key point, assumptions is used to constrain the behavior of design input. So we are going to write assumptions on inputs directly. Next. So importance of constraint in formal verification. What I told you, that we will have 2⁻m combinations of input, but not all the input combinations are legal. Therefore, we use constraint to restrict input from taking illegal combination. So this is our complete design space, in which all the combinations are not legal. So after adding constraints, it will get into some legal states. So now we have to not cover this complete scenario. We will cover this much scenario only in formal. Okay. So now it's not like you can write n number of constraints. So writing constraints has effect on formal. So if you write too much constraint or over constraint, it will make the formal analysis very small. So it will not cover the complete legal state, and it is possible that you might miss a bug. But if you don't write, if you write very few constraints, it will also cover illegal scenarios, and your assertion will fail because of the illegal scenario. As we saw in our first slide, where the waveform was behaving wrong because of the done 1 and done 2 getting high without sending a request. So we are going to write constraint, but we should make sure that it should not be over constraint or under constraint. So how to write constraint? So we write constraint on the input signals to restrict it. So we have rec, done 1, busy 1, done 2 and busy 2 as our input signal. So we will write a constraint for the rec signal. So we know that rec or a request can only be sent when the interface is free, that it is not busy. So rec will be only sent if the interface is not busy. So this is our, I will say it's an expression, and how we make it into an assumption by writing assume property. Rest all the things are names, name of the property. Here we just write assume, block dependency, and the expression. Any questions?
So for Google, we require the database. So property needs any database?
I told you that it needs the design space, right?
Design
So it will explore the design space and it will check if what you have written is correct or not, and it will show you the waveform for it.
It follows the syntax of which language or something?
This is system level.
System.
Yeah.
And when we say that it is comparing something that your output is correct or not, so what will be the reference point for?
Okay, so for reference point, I just say we write it from the specification. So you have to read the spec of your design, and from that you check that what are the rules for the inputs.
So like morning she said like we will have few sets few criteria designed for specification, and to that criteria we are every time matching that whether our output is correct or not. Is
Correct,
it like
correct.
this?
Yeah.
So formal will also be work on same concept.
Correct. So your question is like how simulation is different from formal?
Yes, I
Yeah,
want to say
okay.
this only.
Okay. So I will tell you. Maybe I can give you some example. Okay. So in simulation, for example, if we have like if you want to drive a signal. So have you written test benches? Okay. So what you use? Either you give a fixed value or you use $random, correct? But formal doesn't require it. You don't need to provide a value or you don't need to provide $random. It will automatically on its own drive any values.
Okay.
So for example, as we have a bus, okay, let's say it's an 8-bit bus. So how many possible combinations are there? 2�8. So formal will drive all 2�8. You don't have to say it that give this value. It will drive all 2�8 possible combinations. That's why we have constraint to restrict it to some values. Like formal को हमें बताना है कि पूरी वैल्यूज मत ड्राइव करो, यही कुछ वैल्यूज हैं जो लीगल वैल्यूज हैं, आपको वो ड्राइव करनी है. So it's in simulation, we drive the signals or we provide $random, but in formal we don't do that. Formal will automatically drive its inputs and it will check if the output is behaving as expected or not.
And in this case, we'll have to check to our inputs also कि उसने सही लिए है.
नहीं, आपको चेक नहीं करना है कि आपको इनपुट सही नहीं, आप खुद से डिस्क्राइब करोगे कि आपको इनपुट क्या देना, तो वो आपके ऊपर है. इसके लिए मैंने बताया कि अगर आप ज्यादा कंस्ट्रेंट डाल दोगे तो वो अच्छे से परफॉर्म नहीं करेगा और कम डालोगे तो ज्यादा. तो इट्स ऑन यूजर हाउ वेल ही डिफाइंस द कंस्ट्रेंट्स ऑन द इनपुट.
Let us say you have a FIFO, and I'm just giving an example. So FIFO can be of two types. One where you expect that okay, over a period of time this FIFO may get full. But there are also FIFOs where weights are matched. Input आया, output निकल गया. So in those FIFOs you never expect it to be full. So you can write an assertion that output, FIFO full should never occur. Okay, so I write
This is as per the specification.
yes, because the rates are matched. Input आया and on the very next block the output is framed. The FIFO never accumulates and therefore it should never overflow.
Yes.
So it is like making a statement first and verifying, and formal will go and verify is that this statement that you wrote
It's true
is true or not.
Okay.
Correct.
So it is like you are telling the tool that prove me wrong if you can.
Yeah.
So it will try and prove you wrong at number of places, and then you have to go and tell him, oh no, please constrain your input to this. Then you compress the illegal states, and then ultimately it will tell you that yes, what you said earlier is true.
Okay.
Like in simulation, you asked we have golden reference to compare. In formal, we don't have that golden reference. We write properties, the statements which are true. Like if this statement is true, then if refresh is sent, that should be there. This is the statement. This should be true for all the scenarios. If formal try to find where this fails. If this
So you
fails,
make a claim and formal will try to prove you wrong. If he cannot prove you wrong, means you are correct.
means the design.
That is the way the design is verified.
We don't have any golden
It is a
reference
challenging
here.
mechanism.
We write those properties.
You are kind of challenging the person that okay, if you can prove me wrong, मुझे गलत prove कर देंगे. So he starts working to try to prove you wrong. So then you go on adding more statements. You are,
Both are doing the same thing, the ways are different. So at the end,
just that this is much more faster because this is mathematical domain, right? So if you have 2 to the power 8 combinations, then writing it in test bench, you take that much time, right? Because you have to force first, then force again. Here it is nothing, it is all zero time. I mean,
And in
it is only one block.
test bench you have to develop all that driver, monitor, scoreboard. In formal, no need of that. Design है, instantiate करो, run कर दो.
okay.
Okay.
But in test bench, for each input combination, we are giving the expected output also. Okay, what about the formal verification?
In formal, you are writing the assertions on output and assumptions on input.
Correct.
So, in short, the formal is not trying to prove your assertion. Formal will try to fail your assertion.
Okay.
He is trying to find out ways where I can break you. And he will give you the point that okay, this is where your statement goes wrong.
So, like in the first image we saw the formal showed us the waveform where the done was getting high. So it shows that आपने तो लिखा है done should be high when busy is high, but मुझे तो मिला कि done high और busy low है. Then after analyzing we found out कि अरे हम लोग ने तो input constraint ही नहीं किए हैं, इसके लिए गलत behave कर रहा है. Then we need to write some constraint on the inputs so that आपके जो assertions हैं, then formal will try to अच्छा ठीक है चलो अब इसने सही inputs दिया मैं अब इसमें fill करने को try करूँगा. Okay? So after writing assumptions and if we run the same property again कि done should be high when busy is high, then formal will run. It will run for some time. और अगर उसको कोई failing scenario नहीं मिला, so it will say that it is passing. What you have written is correct for the given constraint inputs. Just a waveform like you sent the request, busy got high, here we got done, and after when more done's come, the done got high. Okay. So
This waveform is from the synopsis FPV tool. if you see the above one, the property got true, we can be sure that there are no scenario in which this case fails.
Means
Like,
after yeah.
we can be with 100, we can be fully confident that the design which we wrote is correctly behaved. Because it tries to falsify this. If it doesn't find any falsify test, the
That green
property
tick,
will be proven.
that green tick means that
That-
last
Upper
statement
one.
is
Yeah.
that he
Yeah.
has not found.
This
I
green
mean, there
tick
can be cases where in
This
very
scenario
complex
is-
design, that is, sorry.
Yeah. So what I was telling that this green tick means the scenario which you are checking that done should be high when busy is high is proven and it is not falsified. मतलब फॉर्मल को कोई ऐसा
ऐसा केस नहीं मिला उसे जहाँ पे ये statement false है.
So you understood what are assertions and assumptions and why we need them in formal and how formal is different from simulation. Any question on that? You guys, आप लोग के लिए तो बहुत नया
This is
होगा.
the latest technique. By the way, by the time you guys reach the industry, this will be the status again. This will be the norm.
Because when I
nobody will
joined
use any
batch, I
traditional-
was also from UVM batch. Like I also know UVM. So 2 years back when I joined, I also came to know that there is something called as formal and how it is different from simulation.
This will become the norm for the industry. No more system Verilog, UVM, nothing. This will be the one that the guide
Yes, but still you can verify.
Right. But ऐसा नहीं है कि आप इसको सिमुलेशन से रिप्लेस कर सकते हो, ठीक है? सिमुलेशन बहुत सालों से चल रहा है, आप उसकी लीगेसी हटा नहीं सकते. Formal is just to support our simulation verification because there are some limitations of formal. We will talk about that in later slides. But what I want to say is that formal is like a helper to simulation verification. It is not to replace the simulation verification. Okay?
So the example that I gave, that designer can use Verilog test bench. So that is not required if they are using formal verifications. So they can catch earlier while they are designing this product.
Yeah. We don't have to wait for the complete test bench to design. We will instantiate it and directly run it. So as a first step, what we do, I will tell you. Like in our industry, what we do. I got a design, correct? So I will directly instantiate it in our formal test bench, and I will just write assertion. I will not even write constraints also. I will just write what are the expected output I want, like what are the expected behavior, and I will run formal. So after running formal, I will get the scenarios where it is getting raw. Okay. Then I will check why it is getting raw, and then I will start constraining our inputs. So it's like assertion लिख के चला दो, then we will constrain the inputs to get the legal scenarios. Now cover. So
Is that always the right process, or is it just?
no. It's like
There is planning and
Correct, correct.
also on
So-
assertions, right? Because
Yeah. So main thing is we have to check the output, correct? But if your spec is evolving, like you're still writing the spec and you're still not sure about the specification of the input. So in early process of the writing spec and design, we can do this method. It's like early process, but that's not the correct way. First, we have to read the spec. आपको लिखना है कि what are the rules of the inputs, what are the expected behavior of the outputs, and then write both assertions and constraint and run forward.
Will it be like black box only? In volume mindset, like in verification particular.
Yeah, it's a black box. We don't check what is
So
inside
only
the data.
specification
Yeah.
based on specification. will be-
Correct. That's why we have to just check what protocol is, what are the outputs, input, and we will run. We don't check what is inside. Verification, guys, don't check what is inside the DOT, okay? Don't write your code, verification code. अच्छा, design में ऐसा हो रहा है, ठीक है, मैं ये भी लिख देता हूँ, match. Verification, no, that's not the right process. Don't look inside the DOT. Remember. Okay, now we will see what's a cover is. So cover is like a special scenario. Like हम लोगों ने पहले देखा कि we need smartphone under 15,000. Now, smartphone with 3 cameras. Then we applied filter smartphone under 15,000. Now we will check cover. There is a special scenario. Like मुझे तो Samsung का ही phone चाहिए 3 कैमरा के साथ 15,000. So our Google will search and it will give list of Samsung phones which are under 15,000. Similarly, in formal, you can write a special scenario like show me a scenario where your output toggles for every cycles. So formal will go to your design space and it will generate a waveform for it. So now let's see if there is a special.
We often use covers to know the design behavior. If there are some corner cases, if I want to check whether the design covers it, we can write cover properties to verify those. Assertions like those are statement, but we can write cover properties if you want to check something. Like as mentioned, FIFO. Where does it overflow and what happens after it FIFO overflows?
So cover properties are used for some specific. So we will write one cover property. So we saw scenarios where we get done for green first, and then we get done for yellow, and then this done get. Now we will see if there is a scenario where both done get high in the same cycle, and then this done gets high. So we will write a cover property for it. Name of the cover property, same thing. This thing only changes in our property or property syntax. Like for assert you write assert, for assume you write assume, for cover you write cover, and then same thing, dependency on block, and then you write what you want to check. If done 1 and done 2 are high in the same cycle. And then when you run formal on this, it will find a scenario where this is getting proven.
Like this cover properties, unlike assertions, it doesn't try to fail. It will try to show you a scenario where these three signals are high.
So cover is like in simulation world, we write a new test case, okay, when full is happening. We write a new test case when empty is happening. So cover property is equivalent to that. You want to see a scenario where a particular scenario is happening, like full, empty, or the done is coming, both the dones are coming together. So it is similar to that. So it is not trying to fail this property. It is trying to find
Status of.
it is trying to find a waveform and it will give where it is generated, and
Marking
he
as
will
done.
and he will show you that okay, I have tested this scenario and here is the proof. This is the waveform. I have tested this scenario.
So it will find a scenario where this thing like done 1, done 2, and done are getting high in the same cycle. So summary. So what is a property? Property is just a Boolean expression which is used by formal to define what we require. It can be of 3 types: assertion, assumption, and cover. Assertions are used to check the output. Assumptions are used to restrict the inputs from taking illegal values, and cover is used to find some specific scenario. And this is that simple. This is very simple formal test bench. Like it's not this simple, but you can get the idea that constraint inputs are assumptions, output we write assertions, and cover property to check some special scenarios. So in short, formal tries to fail the assertion and it tries to cover the cover properties. Next slide will be explained by Sam.
We are going to see what involves in the formal verification environment. As in UVM, we will have multiple stimulus-driven drivers and the golden reference to compare. But whereas in formal, we will have the RTL design, the DUT. We will fetch this to our FDP, and we will have the user-defined assertion, assumption, and covers. Assertions would be written on the output, whereas assumptions are written on the input signals to control those scenarios. And we will also write some covers to increase this convergence. We often follow this standard procedure, like we need to have these covers in order to understand the design better, and it also increases coverage. All these 4 would be fed to our forward to FPV. Then after we run this, we will get our status, like as I explained earlier, proven or false, right? Assertions still would be proven false, right? If the proven is, if the assertion get proven, we can be sure that all the legal scenarios are exercised and design small works. If there are any failure scenarios, we will get one waveform, failure trace, we can see and debug it, and we can update the design or the assertions based on the traceback or the debugging view. And we will see how the simulation, we will compare the simulation with formal. Simulation, as explained, it is not so exhaustive to simulate all possible all possible states. We will try multiple stimulus to cover all the state spaces. But whereas formal, it explores all the possible states. It will cover each state itself. And in simulation, it focuses on the scenarios and it only reports if the assertion fails in the design. But whereas in formal, this is a shift focused intent on the behavior change. It will try to falsify the assertions. You can see the setup time required to develop the test bench in simulation is very high, and whereas formal we can start early in the design. You can see the graph here. This red one indicates the simulation where the setup time is high and it takes some time to develop the test case, but whereas in formal, the green signal, we can set up early and find the bugs as early as possible. So the formal enables shift left focus. Like less setup time is required and we can find early bugs as many as possible. So in simulation, we require vector scenarios to simulate the design, but whereas in formal, no stimulus is required. As discussed earlier, we only require just proper constraints based on the design specification. We are likely to miss some corner cases bugs because we are manually typing all the stimulus. But most of the corner case bugs would be caught in formal verification since it explores all the steps. So in simulation, if there are any failures, we will get to know it at the end of the design after that whole transaction is completed. But whereas in formal, we'll have this property, it will point out to the root cause of the bugs. Like we don't need to see the whole scenario. It will point out the root trace, and we can debug from there. Yeah. As always. Anything will have its limitations. So there are some few limitations of formal too. We are going to see it. So this is with the formal property. It's limited by design complexity. These are very hard to verify the complex designs because we need to write many property statements for assertions. So which would be difficult for the complex designs. So we need to take the projects which don't have much complex designs, and it also hard to verify design which doesn't have a documentation or evolving documentation, because based on these documentation itself we are going to write constraints. If we don't have it, the design documentation would be changing. We would be changing constraints over and over again. If we have a clear documentation, we can specify constraints based on that, and we can see the failure scenarios if the design is handled.
So as I told you that in the early design cycle where we don't have proper constraint, we can start with formal and then as we develop we can write constraint and.
But this goes against my policy where design documentation is step number 1. So
Yeah.
I agree.
the design documentation, by doing this, we are allowing designers to come up with designs without documenting.
No, we will tell them that this is incorrect.
We will write
So it is a verification that don't leave designer easily.
And it also hard to verify if there are many more constraints. The example we have seen is a done handshake, which is a simple protocol. But in real life, we will have much complex protocols than this. So we want to define formal what are the legal behaviors in form of constraints. That also gonna take, even if we have design, but it would be difficult. This indicates the types of assumptions we will be having. We can have a simple spec where the whole behavior is legal. Then we can have, there would be 2 modes, only one of the mode is enabled. So this would be a simple assumption set. But this comes a complex assumption set. Even within in the documentation, there are many legal inputs, many more sequences which are we need to provide it to formal in order to verify all the outputs. This is required. If we don't have this, it will just point out where the legal behavior is not correct. So in summary, we have seen the formal verification, which is one of the verification techniques. Unlike simulations, properties are written to verify the design, and property is an SV expression that designs a design requirement. And these can be of 3 types: assertion, assumption, and cover. Assumptions are constraints, we use it interchangeably. Assertions, these are to verify the output behavior. Assumptions to control values of input signals, and the cover to observe any specific scenarios we have. Yeah, any questions? I know this is a new topic.
So this FDP, is it a tool comes under synopsis of
Yeah,
the-
yeah, FDP is to
It's a
synopsis.
different tool, but it's a different tool.
Yeah.
Formal.
How to know that we have covered all the scenarios and assumptions?
Yeah, there we have something as cone of influence, like as in coverage in simulation. We also have something similar in format. We would have a sign-off process where we check whether we covered all the legal behaviors or not. That's the final step to make sure that the design is legally exercised. That comes in the next purpose for verification.
How to decide the complexities after this the formal verification is not that suitable. So how that is generally being decided?
Yeah, generally when in the industry we have multiple specifications and we would have multiple models. So we will see whether the model is feasible to verify with formal or not. The earlier discussion would happen. If it seems it is feasible, then we will go ahead with formal, else we forward with the simulation.
So major projects doesn't solely rely on formal verification. They are combined with functional verification and code coverage and all those things are involved. Right now, major specifications or projects, they use this as an earlier detection of any bugs that we have.
Mostly for early stages.
Yes, yes. And in that process, we can speed up the process of the whole cycle.
If we can also see if the model is very big and we have to verify with formal, we will split the models into parts and then verify in the model level, not on the whole top because it takes it's very complex to verify on the whole top.
So the advantage of formal over simulation is it's fast. Like the simulation might take 1 or 2 hours to run. Formal will give you a failing scenario 20 or 10 seconds. So as the complexity increases, the formal to find a failing scenario also increases. So as you mentioned, the cone of influence is something depth of formal. So as the complexity increases, it is hard for formal to find the failing scenario. So
And here there is nothing like, I mean, so basically it is, if you missed writing assertion on the output,
Writing is difficult, not
it's
easy. But actually it is very difficult task to write a
there is
correct
no
property.
tool to point out that assertion on this output is missing. So it is, very human, like in coverage report, you get to know that okay, I didn't test this scenario. But in formal, if you miss out writing an assertion on an output
That will be.
it will be missed totally.
We should have clear understanding of the design and what are the outputs and what to verify.
But I mean, even if I do, but गलती से mistake हो गया. Missed the assertion, let us say.
नहीं the question was same. हम वही डिस्कस कर रहे थे कि किसी अगर इनपुट का कंडीशन भी इवन कंस्ट्रेंट नहीं डाला तो भी वो भी मिस आउट शायद हो सकता है.
Constraint is different. Constraint is
Constraint वो आ ही
different.
जाएगा, वो
Constraint
generate
तो
कर ही
input.
देगा, input generate कर ही देगा.
Constraint
But the
is
assertion is more important. Assertion works as a checker or identify the issue.
That's true. In general, we will take the model level and we list out the inputs and outputs. Outputs, we should have a clarity what do they do. We write outputs on, we write properties on each of the outputs. Like we don't miss anything.
I'm not saying you miss anything. Just like just like coverage is a tool.
That we will have inside.
You don't have a coverage metric. All outputs are covered or something here.
We would have that sign-off process. We will also have that cone of influence. There is something called as formal code, which says there are this number of outputs. It will compare the assertions we wrote, and it will give us that ratio.
Okay.
Yeah, we check this before we signing it off. Any other questions?
So ये coverage वाला चीज़ है, तो इतने सारे permutations combinations होते हैं, ठीक है, और अगर सब में coverage डालना So इसका report and manage करना वो कैसे मतलब क्योंकि simulation makes very simple to manage coverage reports. But formal में हाँ but
there is one more formal coverage analysis FC
okay.
that generates the coverage report. Same as
Only for the cover points you have written.
You have written.
no, or for all those. That app is called as coverage analysis.
So even if you are not writing cover on properties, they cover everything. They check everything, analyze how to.
I mean, let us say I did write a cover property. Will it itself reading? I mean, how will
It reads as inputs, output, it matches the inputs. It takes that coverage.
Coverage for coverage, you have to add coverage for the property, right?
Cover properties are.
Cover properties.
That's right.
Yeah, so that iteration will be always there. Even if you are using coverage analyzer.
Yeah, but it also considers inputs and outputs. It's not like only checks on the cover.
in summary, if I miss out the cover property, is there a tool to flag? You missed the cover property.
No. That's like transporting spec into cover properties.
I mean, at the end, everything has to be.
Yes.
And these verification tools are having compatibility with the other softwares, right? With any other type, other than the Synopsys. Whichever are the backend tools. They are having.
You are asking if these tools are used out of Synopsys?
Yes.
Yes, they are widely used.
Yes, no?
License.
But
License is
License
right.
only,
But
but
if
is it
somebody-
compatible?
No, not compatible with cadence might have a slightly different.
Difference,
That's
yes.
what I was
But they are using SVA as, I mean, the source code is, I mean, like, if you write a assertion and cover property, because it is SVA.
Yes.
Okay.
So basic language is the same. It is like Verilog simulation, whether you want to run on cadence or whether you want to run on Synopsys, you will get the same result. But they might have a slightly different procedure, we have a slightly different algorithm, something like that.
Likes needs to be different. So the scripting part that I was talking, that collecting coverage or those commands should be different for each tool. So those things differ. But the code, actual code, that is consistent. Yeah.
Any other questions? Any other questions?
Thank you.
One question, whenever we are talking about the verification, so you told me the first who I did this formal verification. So just let me know how many different verifications we are going ahead till the end of our design. Means first formal, then like.
Is it something
Standard trend. It depends on project and how we want to approach with the cycle. If deadlines are there, if we want to speed up the process, there are a lot of things that needs to be considered when you are planning. So at that stage, you have to decide what to do to speed up the process and meet the deadlines.
And student point of view, was the same person involved in functional and formal or the team is totally different?
Usually teams are different, but they can adapt. I mean, it's not like you are focused in one area only. You can't.
Like that, they told me that formal verification happens very fast. So, the काम हो गया, you know,
Designers also get involved in verification. It's not like a single role is focused for something specific. Usually it's specific, but it's not always specific.
The simulation is there, that would be there, and along with the simulation, we have formal.
See, the challenge here is one test bench can